or there were 10 questions and the time allotted is 15 minutes. And I really hope that you have answered or try answering these 10 questions within this given 15 minutes. So from today onwards, I'll be not writing the entire question and option on the board. I'll be projecting the image of the question once again while giving the solutions, and then I'll be directly giving the solutions. Okay, so that's where I think more efficient. Otherwise, it is really time consuming to write the entire question once again and to write the options also. So now you can see the question on the board. So anyway, I'll read the question for you. If P is passivation, Q is N-well implant, R is metallization, S is source drain diffusion, then the order in which they are carried out in the standard N-well CMOS fabrication is dash. Various options are given. Now, for the case of a N-well CMOS fabrication, the following steps are in the order. First one is, it is N-well implant or implantation. Then second one is source drain diffusion. Then third one is metallization. Metallization is the third step. Fourth step is passivation. Okay. So if you want me to do a separate video on the CMOS fabrication process, I'm actually planning to do one. So if you want me to do a separate video, please do mention in the comment section. Okay. So this is the order. Now, what is N-well implant from the question? It is Q. Then source drain diffusion, it is S. Then metallization comes as R and passivation as P. So what is the order? It is Q, S, R, P. This is the order of the N-well CMOS fabrication process. So this actually the various steps were given in a jumbled up order, and you have to find the correct order, right? So this is the correct order. So I really hope that you understood how to do this question, or what was the content of the question. So you should be aware of the CMOS fabrication, generally N-well and P-well CMOS fabrication process to answer these type of questions. Anyway, the correct answer for the first question is option B is the correct answer. Okay, so the correct order is Q, S, R, P is the correct order of N-well CMOS fabrication process. Okay. Next is question number 2. The question is from analog electronics session. It is connected to amplifiers. I'll read out the question. Anyway, you'll be seeing the question on board. An amplifier without feedback has a voltage gain of 50, input resistance of 1 kilo ohm and output resistance of 2.5 kilo ohm. The input resistance of the current shunt negative feedback amplifier. So we are actually constructing a feedback amplifier with the amplifier and a feedback circuit. Okay. So the input resistance we need to find of the current shunt negative feedback amplifier using the above amplifier with a feedback factor of 0.2 is dash. There are various options given. Now what are the given data? First one, the input resistance is given as Ri is equal to 1 kilo ohm. The gain of amplifier A is equal to 50. Beta, the feedback factor. When we are constructing a feedback circuit, we need a feedback factor. The feedback factor is 0.2. Now, if you are constructing a feedback circuit, so we are actually constructing a current shunt negative feedback circuit. So what is the resistance of this feedback circuit? So we are going to find the input resistance of the feedback circuit. So RIF is equal to the input resistance by 1 plus A beta, where Ri is 1 kilo ohm, A is the gain of the amplifier, beta is the feedback factor. So since we are using a negative feedback, this is plus. If it is a positive feedback, then it is minus. That are basic concepts. Okay. So this is the equation for finding the input resistance of the feedback circuit. Now we need to just apply the values here. 1 kilo ohm by 1 plus A is 50, beta is 0.2. So the answer we are obtaining here is 1 by 11 kilo ohms. Okay. So Is 1 by 11 kilo ohms, and the correct option is option A is the correct answer. Okay. So from the given options, option A is 1 by 11 kilo ohms. I hope that you understood how to do this question. We are actually creating a feedback circuit, which is a negative feedback circuit with an amplifier and a feedback circuit. The feedback factor is directly given to you. The amplifier's gain is given to you. You need to find the input resistance of the feedback circuit. For that, you need to find the input resistance of the amplifier. That is, you have to take the input resistance of the amplifier by 1 plus A beta. A is the gain of the amplifier, beta is a feedback factor. So the answer obtaining here is 1 by 11 kilo ohms is the answer obtaining. So in order to solve this sum, it is very easy. 50 into 0.2 is 10 plus 1 is 11. So 1 by 11 kilo ohms. It is very easy to calculate. Correct answer is option A is the correct answer for the second question. Next question is from ADC session, or actually it is connected to quantization, you can say. Okay, a sinusoidal signal with peak-to-peak amplitude of 1.536 volt is digitized into 128 levels, that is quantization levels is given, using a mid-rise uniform quantizer. The quantization noise power you need to find. Okay, so first we need to find the quantization step size. You can call it as delta. It is the quantization step size. You can either use this delta or this delta. Most commonly you will use only this delta. Delta is equal to full scale voltage VFS by number of quantization levels. Okay, or full scale voltage or peak to peak voltage. Okay, by L, which is the quantization levels. Now here in this question, the quantization levels is 128 and the peak to peak voltage is 1.536. Directly it is given. Okay, 1.536 is the peak to peak voltage, and if you solve it, the value obtaining is 0.012 volt. Okay, so this is the quantization step size. This is the step size of each level. Okay, now how to find the quantization noise power? Quantization noise power is given by quantization noise power is equal to delta square by 12. Okay, so this is not actually, okay, this is delta, right? This is triangle. Okay, del square by 12. Okay, or you can use the smaller delta if you want. Okay, anyway, so del square by 12 is the quantization power. Anyway, just know that this delta is the quantization step size. Okay, now what is the value? 0.012 square it is by 12, and from this by solving this you will be getting 12 into 10 raised to minus 6 volt square. Okay, since it is a volt square, you will be getting 12 into 10 raised to minus 6 volt square, and the correct option is option C is the correct option. So here, in order to find the quantization noise power from the given data, you need to first find the quantization step size. Okay, quantization step size is equal to full scale voltage by number of quantization levels, or full scale voltage, you can say it is peak to peak voltage of the signal. Here it is a sinusoidal signal, so it is 1.536 by 128, and quantization noise power is del square by 12. I got a little bit confused with this delta, that's why I'm using the small delta. And we just know that it is the quantization step size. Okay, quantization step size square by 12, and from that you will be getting 12 into 10 raised to minus 6, which is option C is the correct answer. The next question, you can see it on the board. It is actually connected to Laplace transform. It is from the subject control systems, asking the final value theorem actually. Okay, so the question is Laplace transform of I of t is given by I of s is equal to, I'll write it on the board, I of s is equal to 2 by s into 1 plus s. Okay, so this is I of s, which is the Laplace transform of I of t. Okay, now as t tends to infinity, the value of I of t tends to dash. So according to the final value theorem, limit t tends to infinity I of t is equal to limit s tends to 0 s I of s, where I of s is the it's a Laplace transform. So I of s is the Laplace transform of I of t, and we are actually taking the Laplace transform. So in the s domain, limit s tends to 0 s into I of s. So this is the final value theorem. Now we have this as I of s. So in order to find what is the value of I of t as t tends to infinity, we only need to evaluate this much according to the final value theorem. Okay, so we'll try to find what is limit s tends to 0 s into I of s. What is I of s? We'll substitute it here. It is 2 by, the value of I of s is 2 by s into 1 plus s, right? Here it is, s and s get cancelled. As s tends to 0, 1 plus s will be 1, right? 1 plus s is simply 1. So it is 2 by 1, and the answer is limit s tends to 0, 2 means the answer is 2. Okay, so the answer coming here is 2 is the correct answer, which is your option C is the correct answer for option or question 4. Okay, so just you should be aware that if such type of questions are coming connecting the time domain and the Laplace domain, you need to evaluate the time domain tends to infinity, or like these type of questions, you need to study these theorems, initial value theorem, final value theorem. This question is actually asking the final value theorem. Okay, so final value theorem is a concept. The correct answer is option C, which is 2. Next question is the 5th question, which is actually theory question. Okay, so in this video you can find questions from medium to difficult level. Okay, so the question is, the noise at the input to an ideal frequency detector is white. The noise is a white noise. The detector is operating above threshold. The power spectral density of the noise at the output is dash. You need to find what is the power spectral density for a white noise. The noise at the input to an ideal frequency detector is white. Then the power spectral density at the noise output will be parabolic. Okay, so the correct answer from the options are actually raised, cosine, flat, parabolic, and Gaussian. For a white noise, the power spectral density is having a parabolic shape. Okay, PSD is power spectral density is parabolic. Correct answer is option C again is the correct answer for option question 5, which is parabolic structure. PSD is parabolic. Okay, the next question is again connected to MOSFET. It is a problem. Okay, you'll be seeing the question on the board anyway. When the gate to source voltage, that is VGS, of a MOSFET with threshold of 400 milliwatt, working in saturation is 900 milliwatt. There is a threshold voltage of 400 millivolt, and it is working in saturation of 900 millivolt. Okay, there is the gate source voltage is given as 900 millivolt, and the threshold voltage is 400 millivolt. Okay. Now, the drain current is observed to be 1 milliampere. That is when the device is working with a VGS of 900 millivolt in saturation. The drain current is 1 milliampere. Neglecting the channel width modulation effect and assuming that the MOSFET is operating in saturation, the drain current for an applied VGS of 1400 millivolt is dash. The question is simple. You need to find the new drain current. The first drain current is given with a VGS 900. The new VGS is 1400. For that, you need to find what is the drain current. That is the meaning of the question. Okay. So first you should know that the relation between drain current, threshold voltage, and VGS is ID equal to K into VGS minus VT square. Okay, so this is the relation. Now, we'll take the ratio of ID1 by ID2 because we need to find the currents First current is given, second current we need to find. We have been given these two values. So is equal to, we can ignore the K since it is a ratio. Okay, I'll cut it out. VGS minus VT, VT is same. So VGS1 square by K again. So this K and K will get cancelled since it is a ratio. VGS2 minus VT square. Okay, so this is a relation. I hope it is clear. So we are taking the ratio of currents. Okay, so what is the first current? Okay, we'll keep this portion as it is. Then what is VGS1? VGS1 is 900 millivolt. Okay, so we'll put it as, since it is 900 millivolt, we'll put it as 0.9. Okay, this is 0.9. VT is same. For a MOSFET, threshold voltage will be same. So it is 0.4. 400 millivolt or 0.4. Then VGS2 is 1.4. 0.4. Okay. Now this is the relation. Okay. So if you solve it, ID1 is 1 milliampere by ID2, and if you solve this session, you can do the calculation anyway. It will be 1 by 4. So when you solve this sum in the denominator, that is, you will be getting 1 by 4. How it is getting, I'll tell you. 1.4 minus 0.4 is 1. 0.9 minus 0.4 is 0.5. 0.5 square is 0.25. 0.25 you can write it as 1 by 4. Okay. Now ID2 we need to find. Just cross multiply. ID2 is equal to 4 into 1 milliampere it is, and if you take the product, it is 4 milliampere is the correct answer. Okay, so from the options the correct answer coming is D is the correct answer. Okay, from the options D is the correct answer, which is 4.0 milliampere or 4 milliampere. Anyway, just you should know this relation, that is ID, drain current or drain source current, is equal to K VGS minus VT square. And if you take the ratio of ID1 by ID2, you have been given ID1, you need to find ID2. Threshold voltage is the same for both the cases. For the first case, VGS1 or the gate source voltage for the first case is 0.9. For the second case is 1.4. It is given in millivolt. Anyway, you have to convert in simple volts. Or in millivolts also you can do. No problem. Then by 1. So if you solve it, you'll get 1 by 4. And cross multiply, you'll be getting 4 milliampere. Correct answer is option D is the correct answer. Next question is the 7th question. It's a very simple question. N-type silicon is obtained by doping silicon with dash. From the options, A is germanium, B is aluminium, C is boron, D is phosphorus. So in order to get a N-type material or N-type semiconductor or an N-type extrinsic semiconductor, to be more specific, we need a pentavalent impurity. Okay, from the options, pentavalent or 15th group elements. Okay, and for getting donor, that is for getting p-type semiconductor or p-type extrinsic semiconductor, we need trivalent impurities, which is group 13 elements. Okay, so from the options given, boron, aluminium, gallium, all these things are belonging to boron, aluminium, all are 13th group. Okay, option D, phosphorus is 15th group. Okay, nitrogen, phosphorus, arsenic, antimony, bismuth, these are 15th group elements. So you need a 15th group element which is donor impurity. These are acceptor impurities. Group 13 elements are acceptor impurities. Group 15 elements are pentavalent and they are donor impurities. And for getting an N-type semiconductor, we need donor impurities or pentavalent impurities. So from the options, correct answer is phosphorus. So if we dop with an acceptor, we'll be getting p-type. Okay. So the correct answer for this question is option D is the correct answer. Question is 8th question, and the question is actually a circuit which is consisting of Zener diode and op-amp and 15 volt unregulated power source and an amplifier. Okay, so these are the elements present in it. It is a regulated power supply is given. Okay, and the question is you need to find what is the output voltage of this regulated power supply. The diode in this figure is actually not representing a Zener diode, but it is given that VZ is equal to 3 volts. So VZ means it has to be a Zener diode. Okay, so you have to consider that that is a Zener diode. Now, how to solve this question? That is how to find the output voltage. Here if you see in the figure, we can find that the voltage at the non-inverting terminal is 3 volt by the Zener diode. Since the Zener diode voltage is connected to the non-inverting terminal, the voltage V plus is 3 volt. And so, due to the virtual ground concept, V plus is equal to V minus is equal to 3 volt has to be the voltage at the inverting terminal also. So, you have to equate the V minus is equal to, V minus is coming as 3 volt, right? So we generally do these op-amp problems by taking these assumptions. Okay. Now we have V minus is equal to 3 volt. Now if you see the inverting terminal, the voltage is actually connected from the output via 2 resistors. Okay. So you have to apply voltage division rule for finding V minus. What is the equation? V minus is equal to 20 by 20 plus 40 into V out. So output is connected via these resistors. So apply voltage division. 20 by 20 plus 40 is 20 by 60. So 20 by 60. So it is 2 by 6 and 2 by 6 is 1 by 3. Okay. 1 by 3 V minus is equal to 1 by 3 into V out. We need to find V out. You can call it as V out, because V minus or the inverting terminal is actually connected from the output session via 2 resistors. So that's why we are applying the voltage division. I hope it is clear. So just cross multiply. V minus into 3 is equal to V out. So V minus is already known due to the virtual ground concept. So 3 into 3, 9 volt is the correct answer. I have already written the answer here. The correct answer is 9 volt is V out, or V0 is equal to 9 volt. Correct answer is option C is the correct answer, which is 9 volt. Next question is again from the transfer functions, or you can call it as from control systems. Okay, let x of t be the input to a linear time invariant system. The required output is 4x of t minus 2. The transfer function of the system should be dash. A 4 e raised to j 4 pi f, B 2 e raised to j minus j 8 pi f. So from the options, if you see the options, you can analyze that the transfer function is actually a function of frequency. So it is only been mentioned in the question to find the transfer function. So you can write the transfer function in S domain, Z domain, or any domains. Generally in S, Z or Fourier domains, these are the general domains which we use for finding the transfer function of a system. Here, if you examine the options are given as functions of frequency. So in order to express a system's transfer function in frequency, it has to be Fourier transform. Okay, so that is the first clue. Now, if you write the y of t, what is transfer function? Transfer function is nothing but output by input function expressed as either Laplace transform or Z transform or Fourier transform. Now anyway, we require y of t. Y of t is equal to 4x of t minus 2. Right. So we have to take Fourier transform. Why we are taking Fourier transform is because the output is given as, or the options is given in frequency as frequency functions. Okay, so if you take the Fourier transform, you'll be getting y of e raised to j 2 pi f 4 into, for is a constant, then x of t minus 2, how will you represent it? You have to take t minus 2, this 2 term outside. Okay, so for that you will be taking e raised to minus 2 it is. So minus j 2 pi f into 2. Okay, then taking the Fourier transform of x of t, x of e raised to j 2 pi f. Okay, so this is the Fourier transform of this particular y of t function. Now you need to take y of e raised to j 2 pi f by x of e raised to j 2 pi f. Output by input. This is called transfer function. Okay, so this is actually h of e raised to j 2 pi f, or the transfer function of this system. Now, so if you take this to this side, it will be 4 e raised to, taking this product, 2 into 2 is 4. So minus 4 pi j f. Okay, so that is the transfer function of the system. Okay, so from the options, if you see the options, it is not given like this. I'll rearrange this term, e raised to minus 4 j pi f. Okay, just rearranging this pi j and all. So you'll be getting this. The correct answer is option C is the correct answer. So this is the transfer function of the system with an output function y of t is equal to 4x of t minus 2. Now we are just taking the Fourier transform, nothing else, just taking the Fourier transform and cross multiplying, or taking the division or the ratio of y of e raised to j 2 pi f by x of e raised to j 2 pi f, and you will be getting 4 e raised to minus 4 j pi f. Okay, so this is the transfer function of this system. Correct answer for your 9th question is option C is the correct answer, which is 4 e raised to minus j 4 pi f. Okay. The 10th question is from electronic instrumentation and measurement session. The bridge circuit is used for the measurement of following components, or following variables, you can say. A, resistance, capacitance, inductance. B, diode, triode, thyristor. C, transistor, thermistor and antenna. D, LED, op-amp and transducer. So this is a very basic question of electronic instrumentation. A bridge circuit is basically used for measurement of basic electronic components values such as resistance, capacitance, inductance. These are the basic components, and its values, if you want to measure, we generally use bridges. Okay, so the correct answer is option A is the correct answer. A is the correct answer here, which is used for measuring of resistance, capacitance and inductance. Okay, so not diode, triode or anything, we don't use bridge. So here we use bridge. Okay, so the correct answer for the 10th question is option A is the correct answer. So I really hope that you found this video useful. 10 questions, I have tried to mix and match difficult questions. Mostly difficult questions were there when comparing to the technical assistant examination standard. And these videos are very, very useful for any locations technical assistant examination. Please do practice it. There are 10 videos already uploaded. This is the 11th one. You can really make use of these videos for your preparation, because the timing allotted and the questions difficulty level is exactly matching. And also I'm trying to include questions from variety of subjects maximum. So we'll be continuing this series till the completion of all technical assistant examination for all locations. Okay. So after this lockdown period, most probably the HSFC examination will be conducted very soon. So please do practice more and more questions. Please do make your preparation more and more. Please make use of this period maximum. So if you found this video useful, please do give it a thumbs up and also share this video with maximum of friends who's preparing for any competitive examination of electronics, not just technical assistant exam, any competitive examination. And if you want more videos, please do subscribe to the channel. Thanks for watching and keep on watching.